Hi, the topic for today's session is ABCD parameters. ABCD parameters are also known as transmission parameters. Transmission parameters provide a direct relationship between the input and output. ABCD parameters are usually used in the analysis of power transmission engineering, where they are termed as generalized circuit parameters. Now you are familiar with the two-port networks. The first section is the input port and this will be the output port. With a two-port network, we can define different parameters. We have already gone through the Z parameters, the Y parameters, other one is H parameters. Today, we are going to explore some of the features of ABCD parameters. I have already said these transmission parameters connects the input port with the output port. That means it provides a link between the input and output terminals. Here, the input port is designated as the sending end and the output port as the receiving end. I think you have noticed one speciality in the current direction. As the output port is considered as a receiving end, its current direction is shown simply as a continuation of the input side. That is, it's taken reverse. In all other cases, it is shown in the other direction. The first matrix represents the values in the input side, that is V1 and I1. And the last matrix represents the output port. And here the speciality in the current direction is highlighted with a negative sign. The parameters that connect the input port with that of the output port is here represented as A, B, C and D. We can rewrite this in the equation format as V1 is equal to A into V2 minus B into I2. Similarly, the second equation will be I1 is equal to C V2 minus D I2. We are now going to evaluate the ABCD parameters. The port that is involved in this evaluation process is output port. We have to open circuit and short circuit the output port. Consider the first case, open circuiting the output port. What will happen if a port is open circuited? We know if we are open circuiting this output port, the current I2 will not get a complete path to flow through. So the value of current will become 0. We'll apply this condition to this equation. As the I2 term is 0, this term will be inactive and the remaining terms are V1 is equal to A V2. Now we can get the value of A as A is equal to V1 by V2. The same condition can be applied to the second equation. Now this term will be inactive and the remaining will be I1 is equal to CV2 and thereby we can obtain the value of C as I1 by V2. So with the first case I2 is equal to 0, we'll obtain two parameter values A and C. A is equal to V1 by V2 when I2 is equal to 0 and C is equal to I1 by V2 when I2 is equal to 0. There is one more step to complete the evaluation process. We are now going to short circuit the output port. The terminals 2, 2 dash need to be short-circuited. When there occurs a shorted path, what happens is both the terminals will be in the same potential. That means there won't be any potential difference. So V2 will be 0. With V2 is equal to 0, the first equation will get changed as V1 is equal to minus BI2. So we'll be getting the value of B as B is equal to minus V1 by I2. And the second equation will be I1 is equal to minus DI2. And the value of D can be obtained as D is equal to minus I1 divided by I2. Now we have obtained the two other parameters B, D. B is equal to V1 by minus I2 when V2 is equal to 0, and D is equal to I1 by minus I2 when V2 is equal to 0. We'll try to name these ABCD parameters. The expression for A consists of voltage terms both in the numerator and in the denominator, and we can call it as a voltage ratio. And considering the direction, we can see that it is from input port to output port. So A can be named as reverse voltage ratio. Similarly, the parameter D consists of current terms both in the numerator and in the denominator. So it will be a current ratio, and here also the direction is from input to output. Then it can be called as reverse current ratio. The expression for B is written as V1 by minus I2. We know the relation V by I indicates that it is an impedance term. And here both the input and output ports are involved. So it can be termed as transfer impedance. And the last one, C is equal to I1 by V2. The relation I by V indicates that it is an admittance function, and as it is having both the input and output terms, it can be called as transfer admittance. By seeing these relations, we can say that the ABCD parameters holds good for defining the transmission characteristics. It defines the voltage or current gain. It also defines the impedance and admittance values. We'll now try to get the ABCD parameters from a network. We're going to solve a question. Find the ABCD parameters of the network shown. This is a simple circuit. We'll try to solve this. We now know that we have to change this output port in order to get the values. First, we'll start with the step open circuiting the output terminal. These terminals are open circuited. This means that there won't be any current flow. So, no current will flow through this 2 ohm resistor. Then we can redraw this circuit without this 2 ohm resistor. Now our circuit is like this. This is our input current, and this will be the voltage across input port, and V2 will be the voltage across the output port. With this case, we'll be getting two parameters A and C. We'll first try to get the value of C. The expression for C is I1 by V2. The numerator is a current term and the denominator is a voltage term. We have already done the questions with Z parameters and Y parameters. We are repeating the same steps as before. As the numerator and denominator are unknown terms, what we are going to do is, we are trying to make both the numerator and the denominator with similar terms. Here we have I1 in the numerator. We'll try to get a relation for V2 so that the numerator and the denominator can be of similar terms. V2 is the potential across this output port, or it can be termed as the potential across 5 ohm resistor. Voltage across 5 ohm can be calculated using the Ohm's law. V is equal to I into R. The current flowing through 5 ohm resistor is I1 current. So we can write it as V2 is equal to I1 into 5. Now the denominator term has become in terms of I1. That means the numerator and denominator are having same type values. By substituting these values, we get it as C is equal to I1 divided by V2. That is I1 divided by I1 into 5. I1 terms will cancel each other and we'll get the final answer as 1 by 5 mho. I by V is an admittance term, so the unit will be mho. We can get one more value from this condition, A. A is equal to V1 by V2. Let's try to get another expressions for V1 and V2. We have already obtained the value of V2 as I1 into 5. So we'll try to get a relation for V1. V1 is the potential experienced across these input terminals. The potential over here should be considered by taking these components into account. We cannot simply write it as I into R. We can write V1 as I1 into Z effective. As these two resistors are connected in series, we can calculate the Z effective value as 1 plus 5. While substituting this value, we will get the relation for V1 as V1 is equal to I1 into 1 plus 5. Now, we have got both the numerator and the denominator with I1 values. In the position of V1, we will substitute the value as I1 into 6, and for the denominator, I1 into 5. So the relation for A can be simplified as 6 by 5. You can notice I haven't given any unit for this term. The reason is simple. A is a voltage ratio. That is, in the numerator and in the denominator, we are having voltage terms. That means ratio of similar quantities will not have any unit. So it can simply be written as 6 by 5. Let's move on to the second case. Short circuiting the output port. Here, these two terminals are shorted and the remaining circuit will be like this. As of a normal network, we can denote the terms I1, V1 and I2. Here, the voltage V2 will be 0. And the two parameter values that we obtain from this condition are B and D. We'll first consider the parameter D. It's having the relation I1 by minus I2. As we don't know the values of I1 and I2, we'll try to simplify it. First, we'll try to get an expression for I2. I2 is seen here. That means it can be considered as the current flowing through this branch. The current that enters into the network is I1. So we can get an expression for I2 using current division rule. I2 is equal to total current I1 into the resistance in other branch 5 divided by total resistance. Here, the current I2 is having current direction opposite to that of I1. So, a negative sign is given. Now, the denominator has also become a term of I1. We can substitute this into the first equation. Here we are having a minus term. In order to avoid a confusion, I am writing this relation as minus d is equal to I1 by I2. We will now substitute the value for I2. Minus d is equal to I1 by I2. It gets simplified as 7 by 5. And this is a unitless quantity because it is having current in both the numerator and denominator. We need to find one more value, that is B. We'll first try to get an expression for V1. V1 is the voltage experienced across the input terminal. So in order to get an expression for V1, we can apply Ohm's law, I into R. But the resistance at the input side is not a single quantity. It needs to be simplified as the effective resistance or effective impedance. V1 is equal to I1 into Z effective. In order to get the impedance value here in this point, we need to calculate it from the opposite side. That means we need to take the effective impedance starting from this point. This 2 ohm and 5 ohm are interconnected in a parallel format. Here it is connected and the other ends are also connected. So it is a parallel connection. This parallel combination 2 parallel 5 is then connected to 1 ohm. 1 ohm and this impedance is connected here, but the other side is not directly connected, so it will be a series connection. You know how to reduce this. The effective impedance of a parallel combination can be calculated as R1 R2 divided by R1 plus R2. 2 into 5 by 2 plus 5 plus 1. We got this from simplifying the expression. 1 by R effective is equal to 1 by R1 plus 1 by R2. So by simplifying, we'll get it as 17 by 7. And we can apply this into this equation. V1 is equal to I1 into 17 by 7. We now obtained V1 in terms of I1, but the denominator here is I2. In the previous step, we have obtained an expression for I2. I2 is equal to minus I1 into 5 by 7. So both the numerator and denominator has become in terms of I1. We'll get an expression for B. The minus sign has been put over here and the expression for minus B will be V1 by I2 and we'll get the solution as 17 by 5. Put the unit as ohm because the expression is V by I and impedance value. So we have got the final answer. A is equal to 6 by 5, B is equal to 17 by 5 ohm, C is equal to 1 by 5 mho, and D is equal to 7 by 5. Thank you for watching.